All right, welcome. In this video, I want to continue my analysis of selection sort. We did a proof of correction in the last video with loop invariant. And now I want to look at runtime analysis. So let's take a look at the number of operations carried out. And this is the code that we were looking at in the last video. Again, a little bit of pseudocode. I maybe won't go through the algorithm, but we are going to go through it sort of line by line to see how many operations we're going to carry out on each line when we execute that line. So going through here again, well, maybe I'll just bring it up here. The first line, usually I'm just going to count this as one operation. It might actually cost more than that, but I call it sort of one method call or one operation to enter into the method. Maybe you count that as more, maybe you count it as 0 too. Maybe we'll just take that as a free option, but I count it as 1. That's a pretty easy one. Moving on here, entering the for loop now. There's nothing really going on before the for loop. So in the for loop, what operations are actually being carried out? Now remember, this is sort of a complicated line of pseudocode that hides behind it, some more basic operations. We know when we hit this line the first time, we're going to initialize I to 1. But if we hit this line any other time, we're going to increment I as we loop. And every time we're going to also do a comparison to this value here, n minus 1. And what that actually means is we're also going to always carry out that minus 1. Now, if you sort of optimize your code, you could do this by maybe setting a variable before the loop, make it set to n minus 1, so that every time we execute this line, we don't actually have to carry out that minus 1. Now, depending on what language you're in, I imagine there are some languages that will already optimize this out for you in compilation or in execution. And then also, well, in modern days, one operation here, one operation there is usually not the kinds of nitpicking we're doing for optimization. We'd rather have bigger optimization that might improve the algorithm altogether. Asymptotically, that is, if we're considering big O or big theta bounds. But if you're sort of an engineer and you're really into high performance computing, then these are the kind of little optimizations you can do that actually will impact the runtime at the end of the day. It won't change the asymptotics, the big theta, but it might change the constants out front, and those do matter when real time is what we're counting. So here I'm using this sort of naive, non-optimized pseudocode. That's fine. You could imagine by optimizing a few of these steps, we'll be able to change some of the constants in our final function, and maybe I'll comment on that when we get there. But for this line, I'm going to count this as 3 operations. The assignment or increment, depending on when we hit this line, plus the comparison and the subtraction that I have here as well. Okay. Next line, one assignment. That one's pretty straightforward. And then entering into the next loop. Again, same sort of comment on this loop. We might, if we were optimizing, we might optimize this plus 1 out ahead. And in fact, in my analysis here, that's what I'm going to assume happens. So I'm going to put that add in brackets. Now, why am I going to assume that here, but not above? Well, the reason is here, that add actually only happens the first time I hit this line. Because the next time I just increment j, I don't go back to I plus 1 again. And so for consistency, I'm going to say, okay, let's imagine we actually did that out in front of the for loop instead, the actual addition, and then the assignment or the increment will count that every time we hit this loop. So I've kind of got that in brackets here because I'm going to bundle it kind of with the line above. Okay, this line, very similar to what we saw in our minimum function. It's got a comparison, and then it's got what happens in the then case, but we have no else case. I'm going to assume this is the worst case, so we actually do go down the then branch. So I think in previous analyses I said and possibly one assignment here. In the worst case assumption, we'll assume that it is indeed being executed. Okay, now we're starting to exit the loops. So remember, when this is just sort of a shorthand that I use. Sometimes I will put 0 operations here, but this is kind of a note to myself saying, actually the way the for loop ends is by hitting this line one last time, where we increment j again, and then it becomes greater than n. So we say, oh, we don't enter the loop and exit down below. So I'm counting those two operations here as my exiting the loop here. Now I think I mentioned this when we looked at bubble sort as well. Swap, we didn't look at the swap sort of subroutine that I'm calling here, and it's probably more than one operation. So I call it one swap here, but if I'm really careful, I could go look at that. It's, as I mentioned before, it's at least usually 3 operations, or maybe more than 3 operations, but I'm just going to count it as one here. Again, that might change a few of the constants. It's not going to change the asymptotics, the big O and the big theta. Okay, so that was the swap. What about these 3 operations? Well, it looks like we're going to do this line again, and I'm counting this as 3 operations, so that's exiting this for loop. And then finally we return, and I just count that as one operation as well. Okay, now to put this all together, we're going to need to put this into summations, as we've been doing so far. And then likewise, because we have nested loops, we're going to end up with nested sums. Okay, so let's take a look at the sum that I've come up with. And let's just see how I've put all the pieces together, which pieces went where, to make sure I haven't missed anything, and just to make sure we see how it all fits together. So the first bit, I've got one operation. That's this first line. I enter the method, one operation by itself. Immediately, though, we enter this for loop, so that's why the next thing I've got is a sum. Now the sum is going to tell me how many operations are carried out by this loop, and this loop goes from I equals 1 to n minus 1, so I use those exact same indices and values on my sum. So I goes from 1 to n minus 1. All right, now we're entering the loop. Everything inside this big square bracket then is happening inside this loop. Okay, so inside the loop, what's going to happen? It looks like I've got 5 operations here. Which 5 operations are they? Well, it looks like this here. We've got these 3 operations. Remember, the first time we hit this line, we'll do 3 operations. Then we'll carry out this one assignment. And then that one little add that I was counting on this line, I'm going to bring it back to this line here and count it as well. So those are my 5 operations here. And then I'll enter into this loop. So because then I entered that loop, I've got another sum here. That's for this sum here. And this sum I use from j, from I plus 1 up to n. So again, you'll notice I just borrow the exact same index and values, j equals I plus 1 up to n. This isn't always going to be as easy as just copying the indices from our for loops, but when we do have a for loop set up like this, it makes it really easy. And then maybe the second sort of point of that is, if I'm designing code that I'm about to analyze, and I know I could set it up as a for loop or a while loop, I might intentionally set it up as a for loop like this ahead of time, so it makes this part a little easier. Okay, continuing, we're in this sum now, so we just looked at setting up the indices for this loop. What about the body of this loop? Well, again, I'm going to have 1, not counting this add, because remember that's only the first time around, and the comparison here, which is comparing to n. And then inside the loop, I'm going to count these 2 as well, reminding ourselves about the worst case, assuming we're always going down the then branch. So what was that? 1, 2, 3, 4. So that's the 4 that I've got inside my body. Now this 3, which is technically not in the sum, which is a little ambiguous here, but it's technically not in the sum. Where did that 3 come from? Well, the 2 operations I need to do to exit the loop, and then the 1 swap. So here, this 3, if we really want to, be careful with it, this 3 is where maybe our swap might inflate to be, 5, 7, something bigger than a 3. But here, we're just leaving it as a 3. Okay, that was everything inside this loop up to the n4, but not counting the n4 because the n4 is exiting the loop. So these extra 3 operations and this extra 1 operation is the 4 that we get at the end. So this is the summation, at least the initial summation, that we've come up with to express the runtime, or the number of operations carried out by our selection sort pseudocode. Now let's see if we can simplify this summation using some of the tools we've used for summation manipulation. All right, so just copying that sum over here so we can work with it a little bit. Let's get started by just gathering some of our terms together so they're not just all over the place. The first thing I'm going to do is I'm going to bring the 4 at the end and the 1 together at the front, and I'm going to leave it out front again because there's a little ambiguity when we write sums. So if we're adding anything onto a sum, we usually add it out front. So now my next sum, I'm going to leave the indices the same. But likewise, as I did outside, I'm going to bring my 5 and my 3 together to get an 8. So there's now a couple ways that we can tackle this. Actually, in the last video, I think what I did is I maybe worked on the inner sum, which is very common. We'll usually do inner sums before outer sums, but maybe I'll just show a slightly different path we can follow this time. We can actually distribute our sum out a little bit more before we continue working. So I'm going to just, well, we'll leave the 5 alone. But now I'm going to distribute this sum into 2 sums. So the first one is just this one here with the 8 alone by itself, and then we just distribute the rest of the sum across to get the nested sum at the end. Now, why might we want to do that? Well, maybe our instinct is to simplify out this sum first. This one looks easier. Let's do it. So let's do that next. We'll bring down the 5 again, but now we'll bring the 8 out front for that sum because, again, 8 does not depend on our I. And now that we've moved it out front, it's easy for us to simplify that one because really when we're just adding 1 to itself, we just need to know how many terms are there in that sum. Well, there's n minus 1 terms quite easily to see there. So we're going to get 5 plus 8 times n minus 1 for this particular sum here, plus, and then we have these 2 sums here, but let's look what else we can do here. 4 does not depend on j, nor does 4 depend on I. 4 is just a constant, so we can bring the 4 all the way up front. Okay, that leaves us with, well, the trickiest sum left. Okay, maybe I'll simplify this one out a little bit more. Let's see what we're going to get. We're going to get an 8n. And then we got a minus 8 here and a plus 5. That gives us a minus 3. So I'll leave that there. But then I have this sum here. And let's be careful. I'm going to, again, when you have 2 sums, you know, you might be clever enough to try and do them all at once. I don't think I am. I'm going to try and do the inner sum first. Now the inner sum is a little bit trickier for us to see here. When we did, which one? When we did this sum here, I said we're just adding a bunch of 1s together. So we just need to know how many are in the series. So I just looked up at the top here, and I saw it was n minus 1. Now that worked because at the bottom, I had 1, and if you start counting at 1 and you start at n minus 1 in this case, then you counted n minus 1 times. But if you started at I plus 1 and you counted to n, you didn't count n times, well, unless I happened to be 0. Okay, and so we need to figure out, well, how many times did we count here, or how many 1s are there really in this series? And there's a little formula we can use. So I'm just going to go to my scratch here in case we don't remember. I think I introduced this in an earlier video. If I didn't, it's one that we can prove. If I have I and I go from A to B, now our instinct, hopefully most of us are saying, well, it's going to be B minus A. That kind of makes sense, except when we do this minus A, we don't count the fact that we actually started at A. We don't count starting at A. And so if we want to count that, we have to do plus 1. And we can see this quite easily. If we plug in here 1, and we plug in here n, and we just did n minus 1, that's not right. It should be n minus 1 plus 1, which is n. So we might check our work here and see that's correct. So the formula, whenever you have this I equals A to B of 1, is B minus A plus 1. So here, our B is n, and our A is I plus 1. So I'm going to rewrite this one now, and I'm going to be careful. What was my B? My B was n, so I get n. My A is I plus 1. It's minus A, and I'm going to be careful, so I'll put it all in brackets so I don't mess up my minus here, right? I plus 1 is my A, and then plus 1 more. Okay. maybe I should do a little scratch again. What is n minus I? I'm now going to do my minus propagated inside or distributed inside to get a minus 1 plus 1. Oh, now we see the plus 1 and the minus 1 cancel, so that just gave us n minus I. So I'll rewrite this. This whole simplified is just n minus I. So we're at 8n minus 3 plus this sum, I equals 1 to n. And what did we say? N minus I. Oh, look at that. I made an error so far, so good thing I was watching as I was going. Looks like we forgot to copy that minus 1 down properly. Okay, when I went from this line down to here, okay, it looks like I forgot my 4 and I forgot my minus 1. And it looks like over here, forgot my 4, I forgot my minus 1. Okay, hopefully if you were following along and you noticed that too and you said, hey, why is that not working? Now we're back where we should be. Okay, so if this is where we should be, then we can continue by distributing this sum like we did above, which is our first step basically when we distributed the sum over. So again, let's keep it going. We got our 8n minus 3 plus 4. The 4 goes distributing along with the sum, so we should be careful. And we're going to get here, our first one here is going to be the sum over n, I equals 1 to n minus 1 of n, remembering my n minus 1 this time. And then the next one I'm going to actually pop the minus out as well. So the 4 comes along, this 4 comes along, and I pop the minus out so we only have a plus I on the inside. Okay. Continuing, I think this sum is probably our easier one. I'm going to actually try and do it all in one step. The first thing we should see is that n can pop outside. That leaves us with how many terms in the sequence? N minus 1. So I'm going to be careful. I'm going to do it in one step, which means I'm being a little quick. So hopefully you're following with me. I've got my 4. The n pops out front, and then the remaining sum just becomes n minus 1 because there's n minus 1 terms in there. And then what about our final sum? Well, maybe I'll just leave it for this version so that I can simplify it in my next step. So in my next step, again, maybe I'll simplify things a little as I go. I've got my 8n minus 3, leave that as it is for a moment. I'm going to get a plus 4n squared when I multiply that out, and it looks like I'm going to get a minus 4n as well when I multiply that out. And then I'm going to get a minus 4 whatever I do with this sum. What do I do with this sum? Now remember, this is an arithmetic series, also known as Gauss's sum, or at least that's what I call it, because I remember a fun proof from Gauss of how it works. And so I usually just remember that. If you can't remember it, go take a look at one of my earlier videos. I do a proof on that sum as well. But it's going to be equal to this, with the minus 1 here instead of a plus 1, because we have a minus 1 here instead of n. If we have just n up here, we change this to a plus, but since it's n minus 1, it's a minus. Okay, and you can verify that. There's a couple fun exercises you can do to verify that. So now it looks like we've just got simplification left, and let's see what we can do. Okay, so I'm going to carefully do my simplification, but I'm also going to gather as I go. I've got a 4n squared here. I'm going to leave it alone and bring it out front. My next one is an 8n and my 4n, so maybe I'll cross them off as I go. My 8n minus 4n, that seems to leave me with 4 more n. Okay, 8 minus 4. And then I got my minus 3. Hey, minus 3, stay where you are. And then let's just spend a little time trying to distribute that out. We're going to get a minus. Hey, let's do this. The 4 becomes a 2 because we can cancel it out here. And it looks like we're going to get a minus 2n squared. Okay, let's make sure minus 2n squared. And then the next one is going to be a minus times a minus. So I should be careful here. That looks like it's going to be a plus 2n. Okay, let's try that one more time. Minus times a minus, and the 2n comes from outside. Okay, so that looks like it's correct as well. So we're almost there, it looks like. We can simplify another step. Now it looks like our 4n squared minus our 2n squared gives us a 2n squared. And then we have a 4n and a 2n together give us a 6n. And then a minus 3. So again, I mentioned, let's maybe reflect on a couple things here. Okay, one was, well, first of all, our goal is to maybe show that this has a particular theta bound of n squared. And maybe, actually, since this is our main goal, let's just do a quick little limit test of 2n squared plus 6n minus 3 all over n squared, which hopefully we, maybe we've practiced this enough already that we can see, okay, how are things going to work out here? We'll cancel out the first ones, we get 2, plus, it looks like we're going to get a 6 over n plus, plus a minus 3 over n squared. This one and this one, those go to zeros, so it looks like we got 2. So check. By the limit test, we've got an n squared function. So that was sort of the main goal. That was the first point I wanted to bring us to, is that this is a n squared function. So bird's eye view, what are we talking about? We were talking about the selection sort algorithm. So now we have a tool to measure its effectiveness or efficiency. It's a n squared running time. Okay, it's n squared running time. In this case, is if we want to have a more finer tooth analysis, we can say it's not just an n squared running time. We have this function here, 2n squared plus 6n minus 3. That's exactly how many operations this version of our pseudocode takes, given the analysis we've given here, noting that we made a few assumptions along the way about our code, about how it was written, about what optimizations were where. Okay, now one of the things we can do, maybe let's go back to our start here and remember where these operations came from. Okay, these 4 operations in the middle, these were the ones right in the middle of our nested loop, and not surprisingly, these are the ones that actually contribute to, it started out with this 4n squared, but it also had this minus 2n squared, but so it eventually gave us the 2n squared. That 4 in there is what it contributes to the constant in front of our n squared. The 5 and the 3 that produced the 8, that was more a factor in the n term, the 6n term. Okay, it gave us this 8n that we were carrying around for a long time. That 8n eventually got knocked down a little bit by the, where was it? We had the 4n, and then we plussed on another 2n over here. So it eventually got reduced a little bit down to a 6n, but most of that effort came out of the 5 and the 3 here. Now let's stop again and remind ourselves that 3 is where that swap was. So let's say that swap wasn't a 1 operation, it was 3 or it was 5. If that were true, we're now up to 5 or 7 here, or this 8 becomes a 10 or a 12. Is that going to end up contributing to the overall asymptotics? Not as much. It will contribute to this second order term or this lower order term, but it won't be contributing to the constant out front here. And that's something that, again, if we need this fine-tune analysis, we can say, okay, that swap, not as bad as we thought, because we're only doing 1 per outer loop, not 1 per inner loop, which might mean it's more expensive. I think that was the only major assumption. We also made a minor assumption related to which branch we took in the worst case. That would change this 4 to a 3, I think, which was not a major change. But that would contribute here to the outer 2. Okay, and then our lowest order term, this -3, is really contributing by the interference by the other stuff, because we started out with just a +5, but where this -1 comes in and then how this cashes out as a -I at the bottom, both of those spit out some minus terms that eventually reduce this down. So I would just call that -3 to be mostly chaos, in the sense that we can't pin it down to exactly where in our code that -3 comes from. It comes from all of the code, whereas as we got up to the higher order term, we could kind of figure out which lines were contributing to that. So by reducing, and so maybe I'll make one final comment. When I mentioned about optimizing our code and moving something that's inside the loop to be before the loop, if we can do that, what that would mean is moving a operation that would be inside a sum here outside. And what that eventually does is move constants from higher order terms down to lower order terms. So maybe by making a few optimizations, we can reduce this 2 to a 1, but it increases the 6 to a 12. And in so doing, when n is really, really big, that's the kind of change in optimization we want. But maybe when n is small, we're actually not making very big savings or any savings at all. Okay, I think that was all I wanted to do for this more in-depth analysis of selection sort. And I want to remind you that if you are familiar with other sorting algorithms as well, then you could carry out the same kind of proof of correctness and then runtime analysis of your algorithms without ever implementing them in code, to just verify their own correctness and ultimately to practice your skills. So when you come to other algorithms maybe that you haven't encountered before, you're pretty confident in your analysis skills. Okay, thanks a lot for watching, and we'll see you in the next video.